Section 5.3, another example of applying Newton's laws. So this is a sample problem. We won't go all the way through it. It says a cord pulls a box of sea biscuits. Why sea biscuits? Who knows? But nice description. Up along a frictionless plane inclined at 30 degrees. The box has a mass 5 kilograms and the force from the cord has a magnitude of 25 newtons. What is the box's acceleration component A along the inclined plane? So this is really just a piece of an overall problem. Typically, we'd have this connected to something else on the other end that's creating this tension force of 25 newtons. But here we want to really focus in on what does it mean that we are on this inclined plane, on this ramp, because it will change some things. So we can follow our typical procedure where we're going to, if we care about acceleration, tension, forces, we're going to draw out our forces. So what are the forces acting on this block? Well, one of them is the tension, as mentioned, and it's going to always pull on the block along the direction of the cord. So we can fill that one in. Cool. What other forces do we have? Well, one is the force of gravity, and what's the direction that gravity pulls? Always straight down. So the force of gravity is going to pull straight down. All right, and then what other forces? It's frictionless, so we don't need to worry about that. We also have the normal force. Now, point with what direction do you think the normal force is? Remember, the normal force is going to be normal to the surface. So not necessarily opposite gravity. In this case, but to be normal to the surface is going to be perpendicular to that inclined plane, sticking out like so. So this is a really interesting one because our tension and our normal force are no longer pointing straight up and down or side to side. So this is a case where when we're analyzing it, we want to switch to rotate our X and Y coordinate axes. So we can line them up with the incline here. Switch to black. So we can have our positive X going up in the same direction as the tension, and then similarly positive Y going out, sticking out from here. So with that, this is now our positive X and our positive Y. We've lined up our coordinate axes with 2 out of 3 of the forces, which is pretty good. The force of gravity, though, notice, is in a direction that is not purely X, not purely Y. So I'm just rewriting where it is to make it a little more room. Force of gravity. So we need to break down our weight vector into X and Y components. So drawing each of those in here, we could say that we have a Y component, FGY, that is pointing into the ramp. The force of gravity in part is pushing the box of sea biscuits into the inclined plane. And the other piece of it is pushing down and fighting that tension. So that would be our FGX. Now, when we're solving these, we're going to need to figure out where that angle fills in to this picture. And this is a tricky part, but the way I like to think about it is that angle describes how much we have offset our coordinate axes from what is normal. So we've offset our x-axis by theta. Similarly, our y-axis is going to be offset by theta. So it normally would be pointing straight down, up and down in the direction of FG, but it is offset by that angle of theta. So find ways to convince yourself that this is true, because this is a key detail, that the theta goes between the vertical force of gravity and the tilted y-coordinate reference frame. Once we have that theta, we now can solve for our other components, right? We can say that our FGY is going to be related to FG with cosine of theta, because now the angle is defined relative to the vertical. So we use cosine of theta for the y component, which is an interesting switcheroo. It still works. And for this x component, which could also be drawn down here, for FGX, notice it is now opposite that angle, and so we're going to use sine. So we can get it with the magnitude of the weight, Fg, times sine of theta. Now that we've identified these forces, in order to get the box's acceleration component along the inclined plane, which will be the overall acceleration A, all that we have to do is go back to Newton's second law, right? That F equals ma. So the net force in what we're going to call the x direction, this rotated x direction, is equal to the mass times the acceleration in the x direction. So if we look at the forces in the x direction, we do have tension, but unlike the last example, it's not just tension. We also have this FGX that we need to consider. The tension is in the positive direction, but FGX is in the negative direction. So we'll add that negative sign. And this is equal to our mass, which is little m, times our acceleration, which is what we're solving for. So FGX, we've already said, is Fg, which we could write as m times g, times sine of theta. So we're just about there. So tension minus mg sine of theta is equal to our mass times our acceleration. So we could divide our mass out, actually. And that will give us our acceleration. And so there we've figured out the component of the acceleration along the inclined plane. It had to do with the net force along the inclined plane, which is in this case tension less by however much the force of gravity is along the plane. And so this is detailed pictorially in the next slide, where it shows all of the forces acting and how we can break the force of gravity component into a perpendicular component in the y direction and parallel component. And using the adjacent and opposite, we can connect that as mg cosine theta, mg sine of theta. And so the net of these forces will determine the acceleration. In the other direction, the y direction, which we didn't look at, the normal force just balances the y component of the gravity, mg cosine theta. So you could solve that the normal force in this case is equal to mg cosine theta because there's no acceleration in that direction perpendicular to the inclined plane. Right, so there we have it. This is all of chapter 5. We will pick up with more forces in motion in chapter 6, so stay tuned.